This lesson is 5.3, Proving Triangle Congruence. We're going to be looking at triangles and how they're congruent, but there are certain properties that we can look at, and maybe we don't have all the information of a triangle, but if we have a certain combination, then we can automatically know that those triangles are congruent. And we can match up corresponding sides and be able to solve problems once we know. So in this one, we're looking at side angle side congruence, or SAS congruence. This theorem is going to tell us that if we have two sides in our triangle, so if you look at this diagram down here, if I have two sets of congruent sides in my triangles, so here I have a 1 tick mark, a 1 tick mark. I have a 2 tick mark, a 2 tick mark. If I know that two sides are the same in two different triangles, I have two pairs of congruent sides, and I have the included angle. Okay? Included angle means that it's in between them. Notice it's SAS. It's not SSA. It's not any other combination. It is SAS. The A is in the middle, so that means that our angle that we're talking about that has to be the same has to be the angle between our two sides, where the two sides meet. So once we're able to determine that we have two congruent sides, we have two pairs of congruent sides, and the angle between those pairs are the same, then we can automatically make the statement that the two triangles are congruent to each other. Even though we don't know that BC here and EF are congruent, and we also don't know if the other two sets of angles are congruent, but just because of this theorem, then I can automatically know the two triangles are congruent to each other. So in example 1, we're going to want to use SAS congruence theorem. We're going to be doing proofs a lot with these triangles. So first, think about a proof. I need my two-column proof. So I need my statements and my reasons. And then I'm going to start off with my givens. So I have BC is congruent with DA. And I have that BC is parallel with AD. And my reason for these are just going to be that they're both given. These have already been marked in my diagram, so I don't have to do anything else there. I'm working towards showing that these two triangles are congruent. I have this triangle ABC here, and then I have this triangle CDA on the other side. And I want to prove that they're the same triangle. In this case, I already know that I have one set of congruent sides. So I need to look for another set of congruent sides and a set of angles that are the same that would be included between those two sides. So when I look at this, let's look at our second statement here. We have that BC is parallel with AD. If they're parallel to each other, think about parallel lines and transversals. Notice if I were to extend this BC and this AD, so I have two sets of parallel lines here, and then if I extend AC to be my transversal, then I can look at alternate interior angles and they will always be congruent. So here I can look at this side of my angle and my alternate interior on the other side. Those two angles would be exactly the same based on alternate interior angles of parallel lines and transversals. So I'm going to write that statement. So I have the measure of angle BAC, for the first one, would be equal to the measure of angle, or actually it's not BAC, I had stated that one wrong. It's BCA, measure of angle BCA, because I'm talking about this angle here, BCA. And then my other angle of CAD would be equal. This is based on alternate interior angles theorem. From that statement, if angles are equal, then I can also say that they're congruent. So I can say angle BCA is congruent with angle CAD. This is based on congruence theorems of angles, but just congruence in general. So now in my diagram I have a side and I have an angle on each one. So I need another side in order to do SAS congruence theorem. My angle would have to be included, so that leaves the side here of AC, and this is actually the shared side of these triangles. So I erase all this to get rid of it. We have this angle's the same, this angle's the same, and my included angle there of CAD would mean that this other side has to be congruent. Well, if you look at it, that side's the same for both triangles. So if the side is the same, that is actually a reflexive theorem. So basically what I write is that AC is congruent with AC based on reflexive property. So now, because I have a side angle side that are the same on both triangles, then I can make the statement that these triangles are congruent. So I have ABC is congruent with triangle CDA. And this would be because of SAS theorem. Side angle side congruence theorem. So now let's look at example 2. Example 2 tells us that QS and RP pass through the center M of the circle and asks us to make a conclusion about the triangles MRS and MPQ. So if these two segments pass through the center of the circle, that would mean they are both like the diameter. RP would be the diameter of the circle, and so would SQ. They're both diameters. That would mean if they're a diameter and they pass through the center, then each side of my M is going to be the same, right? This would be the radius, this side would be the radius. M is basically cutting in half, it's bisecting it. Same thing goes for R and P. We have a radius and a radius. The radius of a circle is going to be the same all the way around our circle. So then we need to think about some other properties in this case. So we have two sets of lines that are intersecting at the same point. When we have intersecting lines, remember it's going to make 4 different angles there, or 4 angles total, but our vertical angles are always equal to each other. So remember they're like our bow ties. So I have this side and this side are going to be equal to each other. So if I have vertical angles, then that would mean that I have a side, an angle, and a side in that order. I have sides, an included angle, and a side. So that means I can make the conclusion from this picture that MRS would be congruent with triangle MPQ. My sides are the same because I can make the statement that MR is congruent with MP, which is congruent with MS, and congruent with MQ. And then I can say that the angle SMR and the angle PMQ are also congruent with each other. In this last problem, we know that RP is perpendicular with QS. Okay, perpendicular means they intersect at right angles. Right now they already have this right angle marked for us. We could do the same thing on the other side that's a right angle. And we know that PQ is congruent with PS. Okay, so that's why it has these tick marks on here. It's already telling us to use SAS. Okay, remember the order of SAS. We have side, then we have angle, then we have side. They go in that order. If I were to like trace around the side of my triangle, if I'm using SAS, I better be on a side, then I hit the same angle, then I hit the other side. So here, I have a side already. I have M, P, and then I have PS are congruent on both triangles. I have congruent right angles here, right? Right angles are both 90 degrees, so those angles are exactly the same. So then I would need another side. I would need this side and this side. In order for it to be an included angle, it has to be touching those two sides. I can't use QR because QR doesn't even touch my angle that I know is the same. Okay, so that one I can't use. And I can't use RS because RS, once again, it doesn't touch my right angle. So I'm looking at RP. RP is the same on both triangles, so once again, like we did in our problem earlier, we have RP is going to be congruent with RP because it's the same exact side. Okay, and our reason for this would just be reflexive property again. So based on reflexive property, we can agree that our PQR is congruent with PSR because of SAS congruence theorem. The reflexive property gave me a side, an angle, and a side. So if you wanted to write it on here, we have a side, then I have my angle, and then I have my side again. Over here I'd have the same thing. I'd have side, angle, side. In that order.